All right, let's dive in. We're talking about a huge leap forward in medical AI today. I mean, a whole new way for machines to understand our health, and it's a real game changer.
Think about your own health. It's not just one thing, right? It's this whole story told in different languages. You've got images, like x-rays, you've got lab results, doctor's notes. So the big question is, how do you get an AI to read the entire book and not just, a single page? And that right there is the big challenge. It's like a giant puzzle, what they call the multimodal puzzle. The data is just all over the place. It comes in so many different shapes and sizes. And the problem is, most AI models today, they're trained to see only one kind of puzzle piece. It's like trying to solve a 1,000-piece jigsaw when you can only see the blue sky pieces. You're never going to see the full picture.
Okay, so let's break it down. Researchers have basically been slamming into 4 big walls. First, just getting the AI to understand how all these different data types are connected. Second, making it flexible enough to handle whatever combo of data you throw at it. Third, and this one is huge, what happens when some data is just missing, which happens all the time in the real world. And finally, the fourth wall, doing all of this without needing a ridiculously expensive supercomputer to run it. So, look, people have been trying to crack this nut for a long time. These older models, they had some clever ideas for what's called data fusion. They were definitely important first steps, but they always came with a catch. You either sacrificed accuracy or the model was incredibly slow and inefficient. It was always a trade-off.
And this is where you can really see the difference. The old ways were kind of clunky, a bit messy. They'd either smash all the data together right at the start and lose a ton of important details, or they'd wait until the very end and miss how all the pieces actually influenced each other. But then you look at Covant's approach. It's this beautiful, streamlined, parallel to sequential design. It's a single, clean pass that gives you the best of both worlds without that massive computational price tag.
Which, finally, brings us to the hero of our story today, Covant. I love this name because it literally tells you what it does. It stands for Cost-Effective, Versatile, and Adaptive Fusion Network. This thing was built from the ground up to smash through those 4 walls we were just talking about.
So here's the secret sauce. It's all about the pipeline. Covant is smart. It starts by looking at a couple of data types at the same time, in parallel. This lets it really grasp what makes each one unique. Then it starts adding more information one piece at a time, sequentially. It's like a detective building a case, right? You get one clue, then another, and with each one, the picture gets clearer and clearer.
Okay, so what's the engine driving this whole thing? It's a brand new piece of tech called the MeHyf layer. That's MEHYF, Multimodal Efficient Hybrid Fusion. This is where the real magic happens, so let's pop the hood and see how it works. The big idea inside this MEHYF layer is something called Hybrid Space Aware Fusion. Now, that sounds complicated, but the concept is actually pretty cool. Instead of trying to cram all this different data into one single box, it learns to see it in 2 totally different ways at the same time. It's kind of like having both regular vision and night vision at once. You just get a much, much deeper understanding of what you're looking at.
I love this analogy because it just clicks. Seeing things in what's called Euclidean space, that's like putting your nose right up to a painting. You see every single tiny brushstroke, all the fine-grained, pixel-level detail. But then there's non-Euclidean space. That's like taking a few steps back. Now you see the whole painting, the composition, the relationships between the parts, what it all means. The amazing part is, older models could really only do one or the other. Covant's, it does both at the same time.
Okay, but let's get real for a second. This is a critical question. In a real hospital, things are messy. You're not always going to have every single lab result or scan for every single patient. So what happens when a piece of the puzzle is just gone? What does Covant do then? Well, it's got another genius trick up its sleeve called the modality mixer. You can think of it like a super smart bouncer at a club. It checks each piece of data at the door. If a certain data type, say a lab result, isn't there, the mixer just says, nope, you're not on the list, and gives it a weight of 0. That means the missing piece has absolutely no influence on the final result. It doesn't throw everything off. It's just incredibly robust.
Okay, so the design sounds incredibly smart, right? But the real question is, does it actually work? Well, let's get to the fun part, the results.
The researchers tested this thing across 16 different public data sets against all the other top models. And honestly, the numbers are kind of staggering. First up, pure performance. How accurate is it? On average, Covant was about 6.1% better than the leading models out there. Now, 6% might not sound like a huge number, but in the world of clinical predictions, that is a massive leap forward. But hold on, this is where it gets really nuts. It got that performance boost while being tiny. We're talking a reduction in model size, what they call parameters, by up to 95%. It's like a tiny little powerhouse. And the 1-2 punch is this. It's not just smaller, it's also way more efficient. It cut the computational cost, the raw processing power it needs, by almost 79%. What does that mean in plain English? It can run way, way faster on cheaper, less powerful computers. So it's better, it's smaller, and it's faster. That's the trifecta. This table really drives the point home. Just look at Covant-SN right there. It's getting the same level of performance as a competitor called LegoFuse, but look at the difference. LegoFuse has over 100 million parameters. Covant does the same job with just 5 million, and it does it using a tiny fraction of the computing power. That bang for your buck, that performance to cost ratio, it is just off the charts. All right, so what's the big picture here? Why should we care that there's a new, more efficient AI model out there? What does this actually mean for us? Let's connect those dots. It all comes down to one word: accessibility. See, Covant isn't just some cool experiment stuck in a lab. Because it's more accurate, because it can handle missing data, and because it's so incredibly efficient, it means that powerful, state-of-the-art AI is no longer just for the big-shot research hospitals with massive server farms. It makes this technology practical for smaller clinics, for hospitals with tighter budgets. It basically democratizes cutting-edge medical AI. And the researchers who built it say as much. They believe this design sets a whole new standard. They've built something that is just fundamentally better suited for the real world, for the messy, complicated, and imperfect data that doctors and patients deal with every single day. So that leaves us with a really powerful thought to end on. What happens when a tool this powerful, this efficient, is no longer locked away in the most expensive research labs? What could that mean for medical care in your community, or in communities that have never had access to this kind of technology before? It's a pretty exciting thing to think about. Thanks so much for tuning in.